satellite gravity gradiometry. Gradiometry means measuring the gradients or second order derivative. So how do we do that? We have a satellite mission GOES which use actually this technique. Look, if I have one accelerometer, I can measure the potential. I can measure the acceleration, and from the acceleration I can take the potential. And I explain, if I have two accelerations, then I have a differential here. You know, if I divide these two, subtract these two, make a difference, I can measure the acceleration difference. Acceleration difference. So, based on differencing, therefore, the high frequencies can be recovered because acceleration differencing is an amplifier. So, if in a satellite, I have a coordinate system inside the satellite, for example, let's see like that, and I have three accelerations, two accelerations along each side, along each axis. So, and let's see. So, they assume that this is a long track. This is the satellite. Is here. It's a long track of the satellite. This one will be radial track, and it will be cross track. So, as you see, a differential accelerometry is happening here. Another differential accelerometry happens here, and another differential accelerometry happens here. This instrument, which has this 6 accelerator or 6 orthogonal accelerator, is called gradiometer. So the gravity gradient is nothing else than the difference between two accelerator measurements. And since the distance between these two accelerators or along each line is known, therefore, in fact, let's say it's around 2 meters, I think. And since this distance is known and the acceleration is known, then the differential acceleration divided by this distance, let me call this delta D, it is almost the derivative of acceleration with respect to derivative of time, respect to d over dd. So, or the second order derivative, as we already showed that this acceleration is actually the gradient of the potential, and this one is also gradient of one, and we have the differential accelerometry, and when this distance is small, in fact we have gradient of the gradient of the gradient, or second order derivative. So in fact we determine, or we measure a tensor, second order tensor. Let me write it T. Let's say V. So I have acceleration along track, if you remember, and potential along track, cross track, along track, radial track. And here is the potential radial track, potential radial track, cross track, and here is the potential cross, and it's symmetric. The same here. This is called gradiometric tensor. Gradiometric tensor. And we have already discussed about gradiometric boundary value problem and how can we determine the spherical harmonic coefficients of the gravity field using the second order derivative. We have already discussed that. But what we can explain here that this the second order is more sensitive to high frequencies. Why? Because the accelerometers, two accelerometers that we have, they are very close to each other, and we will discuss that when these measurements are closer to each other, the sensitivity to higher frequencies of the gravity field increases. So this is the principle that it is used in both satellite mission for recovering high frequencies of the gravity field. The measurements in the spherical harmonic coefficients are, for example, I write one of them, the first one, which is the radial direction or z direction. It's 1 over r2. I think I have already written these equations for you in the first chapter of our discussion, or one of the beginning chapters. But here I just explain the second order radial derivative, theta and lambda. So the second order radial derivative, as you see here, we have a term here, which is actually, here you have a upward continuation factor, upward continuation factor, or damping factor. And we had already discussed that when R is larger than R, this ratio will be smaller than 1, and when it gets power n, it gets smaller and smaller. And when it gets smaller, when it is multiplied to Vnm, it will kill high frequencies. So taking the second derivative, actually, you see, when n increases, this ratio decreases, but n plus 1, n plus 2 is multiplied to this ratio. So it will amplify this term. It causes that this term doesn't let that this R over R kills high frequencies. It will reduce this power. This is why that you can recover higher frequencies of the gravity. The main issue here is just to measure this one that I explained, that this comes from differential accelerometry. In fact, this differential accelerometry, measuring acceleration here, which is the derivative of the potential here, and this derivative of the potential, and putting two accelerometers in that direction with the specific distance d between, is in fact a practical way of taking derivative. Yeah, derivative is nothing else than the ratio of the difference between two quantities divided by the distance between the quantities. That's all. But it is inside the gradiometer. It means that the gradiometer directly measure this second order derivative of the potential. And how does it work? Based on differential. But if you just explain a little bit in mathematics, if you remember, it was the f of x, and if I have a function somewhere, definition of the derivative, what is? And if I have a small delta x here, and we have fx here, I can write fx2, for example, here x2, and here is x1, and here is fx1. I can write fx2 minus fx1 divided by x2 minus x1, or delta x. And in the case of differential accelerometer, we have delta v2 here minus delta v1. It's exact, this function represents this one, and this one is here. And this is the definition of, I will write delta f and delta x. This is the definition of derivative, but the derivative means that I take the limits when delta x goes to 0. However, in the size, comparing to the size of the Earth, the gradiometer with 2 meters, for example, the separation between the accelerometer is almost 0. Or it means that this distance, or distance which is around 2 meters, is almost satisfies this condition. So this means that the derivative is measured by this way. The specific distance between the satellites, this in the accelerometer, and each accelerometer gives the derivative of potential, and by differentiating and we dividing with the distance, which is now actually is in fact you are taking the second order derivative of the potential. And the second order derivative, as we explained, is more sensitive to high frequencies.